Okay, so we're going to be talking about linear first-order differential equations and a technique for solving them. So let's take a look at the kind of standard form for linear first-order differential equation. Oops, linear first-order. And so the types of differential equations we're talking about are those that can be put in the form y prime of t plus p of t times y of t equals g of t. And so you'll see here that we have two arbitrary functions of t. Now, the way to solve this is to consider the following. We're going to make an observation. Suppose I take y of t times e, let me call that a capital P of t power, and take the derivative. What's the result? Well, I would have to use the product rule, and so I'd have derivative of the first function times the second function plus the first function times the derivative of the second. That's capital P. Okay. Now, if I factor out that e to the pt, you'll notice something interesting. And that is that this expression is almost identical to this expression. And it would be identical if what? Identical expressions if capital P prime of t is equal to small case p of t. In other words, can we solve this for capital P of t? Capital P of t is the integral of p of t dt. Okay, so therefore we now have a technique for solving a linear first-order differential equation. Let's see how that goes. Now, just to summarize what we've observed now, and our observation is now that if I take y of t times e to the integral p of t dt and take the derivative, I end up with, I'm going to go ahead and factor this out, times y prime plus p times y, which is exactly our left-hand side, which is right here. Okay, and so why is that important? Well, let's see how this is going to work now. So I'm going to start off, this is our integrating factor technique. And this e to the exponential, or e to the integral power, is going to be the integrating factor. We start off with our differential equation, y prime plus py equals gt. I'm suppressing the t on our equation there. Multiply both sides by e to the integral of p of t dt. And now we're going to replace the left-hand side here by the single expression y times e to the integral p of t dt prime. And this computation is why we use an integrating factor. Because at this stage, we now have that the derivative of an expression is a function of t. Okay, so this is the step that's kind of the critical step in solving these problems. Because once you have that an expression is a function of time, then how do you solve for that expression? You integrate it. right? And now at this stage you can solve this for y. Good. So let's see how this works in practice. Let's go ahead and see if I can. Why isn't my? There it goes. Let's go with maybe an easier one first. How about something of the form? How about just y prime equals 2y plus 1? We already know how to solve that. Do you remember how to solve that? C e to the 2t minus b over a. Let's see if we get the same solution now using our integrating factor technique. So the first thing is you want to write this in standard form so that you can identify your p of t. And so the integrating factor is now e to the integral minus 2 dt, or e to the minus 2t dt. Oops, sorry, e to the minus 2t. Multiply both sides by e to the minus 2t. Y prime minus 2y equals e to the minus 2t. Now, again, the whole purpose of this computation was to be able to write this as y times e to the minus 2t prime. And now we integrate both sides. And here, don't forget your c. At the time of integration, you want to add in your c, because that's going to be a critical piece. Because now we can solve for our y of t. Y of t is going to be minus 1/2 plus c e to the 2t. Is that the same thing we had before? Yes, it is. Very good. Okay, let's do one more that's maybe a little bit more complicated. How about y, so we'll solve. Y prime is equal to oop. Let me rewrite that. I'm looking at the wrong problem. Ty prime plus t plus 1 times y equals t, with y of natural log of 2 equal to 1. Okay, so first off, we need to put it in standard form. Oops, that's a plus sign. T plus 1 divided by t, y equals 1, and our initial condition is still y the natural log of 2 is 1. Good. Okay, so now we have our p of t, and so now we integrate. That's e to the integral t plus 1 over t. To integrate that, you just actually do the division, so that's e to the integral 1 plus 1 over t. So that's going to be e to the t plus the natural log of t. And now that's going to be equal to e to the t times e to the natural log of t. And please remember to simplify this. It gets a lot of people. E to the natural log of t is just equal to t. And then we have our t to the t. So this is now the integrating factor. And so what do we do with our integrating factor? Multiply both sides of our equation by the integrating factor. Now, once you get the hang of this, you don't actually have to write down this step, but it's worthwhile to remember that that's what you're doing, because now the left-hand side becomes y times te to the t, and the right-hand side becomes te to the t. Good. And now we have to integrate that. How do you integrate that? Oh yes, the integration by parts using a table. Oops. Did you watch our video? Did you see Edward James Olmos? I liked him better in Battlestar. So y times te to the t. is equal to t e to the t minus e to the t plus c. Good. And now we have our solution. Y equals 1 minus, what is that going to be? 1 over t plus, how do you want to write it? C over t e to the t. Okay, so now we have the y of natural log of 2 equals 1, so we can go ahead and put in our numbers. E to the natural log of 2 is just going to be 2, so this is going to be plus c over 2 natural log of 2. Okay, and so, well, you could finish that up. Solve for c. I'm leaving it there because we're at the 11-minute mark. So I'll come back with a couple more comments and maybe a couple more examples from homework.